Hello, this is the third video in a three video series for load computations. Again, I am Jacob Bender, your guest lecturer for this. I'm going to go ahead and say now what I probably should have said at the beginning of the first video. I am not by nature a public speaker, and that may be obvious from the previous videos, but thank you for bearing with me all the way up until this point. I'm going to have a bunch of ums and ahs as I collect my thoughts and try to go through explaining some of these problems. But I'm very willing to try to help out with these as best as I can. If you have questions in the future, again, I'm going to give some contact info to Crystal so that you guys are able to reach out with questions, and I'll do my best to explain things how I can. Today, we're going over a few example problems from your actual textbook itself. I'm going over about 4 problems total. 3 are on the heating side, 1 is on the cooling side. Unfortunately, the cooling side, several of the questions are relying on tables that are only found in the book, at least as far as reference points go. So I don't have those on hand with me, but I can give you an example that's worked through here of the method that it goes through, and pretty much everything from that point should be working along the same lines. So the first piece that we're going to deal with are heating degree days. This is fundamentally equivalent to your delta T in the Q equals UA delta T equation. When you're calculating HDD, heating degree days, you're taking the base temperature in the building and subtracting the average of the exterior high and low conditions. When you put your HDD into your heat loss calculation, you're going to multiply by 24 in order to convert it from measuring in hours to measuring in days. If it's just asking you to calculate the HDD, all you're doing is calculating that temperature differential. If you're calculating your loss for using the heating degree day method, that's when you're doing Q equals UA HDD times 24. So example problem from the textbook, you're looking at calculating the number of simple degree days in a day if the high temperature were 40 and the low temperature were 0. You're doing it 3 different times with a different base temperature at each time. The base temperature is your inside. So what I said was you're looking at your base temperature, inside temperature, minus your average of high and low outside the building. So in each of these cases, high of 40, low of 0, your average temperature is going to be 20 degrees. So with a base temperature of 65 degrees, if you subtract 20 from it, you get 45 degree days. Base temperature of 60 minus 20 degrees, you get 40 degree days. And base temperature of 55, subtracting 20 is going to be 35 degree days. Again, if you were looking at your heating loss for those components, then you'd be putting in the degree days in place of your delta T in the Q equals UA delta T simulation, and multiplying by 24 to get your total quantity. With soil and having your losses and external walls, these are 2 charts that are also on the slideshow that go along with your textbook chapter that you have access to. It goes with your depth below grade and the heat transmission to the wall in those aspects. And you can see in each of the cases, it's got a column for uninsulated and then 3 different R values that are in place. This is the number that's in those columns is going to be the U that you're putting in your UA delta T equation. You'll notice that the amount decreases the further down you go. So at this profile view, you're going to have the most impact in the top feet below grade, and less coming out at your further below grade levels. You're most likely not going to be dealing too much with values below 8 feet in grade with basement level. And below that point, it's not really a substantial amount. So you may not even really bother factoring that in overall. So example problem from the book, you're using Q equals UA delta T to get your BTU per hour for each zone and add it together. So if a building has a 9-foot deep basement wall that is 160 feet long, the wall has no windows. On average, 8 feet of the wall is below grade, is underground. It gives you outdoor air temperature of 10 degrees, inside temperature of 70 degrees, and an average ground temperature of 45 degrees. So the first part is determine the rate of heat loss through the wall below grade if it's uninsulated. So you come back and look at your tables from the presentation and in your book, and everything that you're doing is in this uninsulated category. So your wall area is being done in sections. So for each one, you're doing the calculation for each foot of depth. So you're going to do pretty much what's shown here. You're going to have a quick calculation for this foot, plus this foot, plus this foot, plus this foot, so on and so forth, all the way down. So 160 feet of width times 1 foot is going to give you 160 square feet of space. So you grab your U value for each of those different grade levels from that column, and you multiply your U times your constant 160 square feet. And then your temperature differential is looking at your inside temperature minus your ground temperature. So in each case, inside temperature is the same, outside temperature is the same. Run the calculation each time, and you can see that as you go further down, it's decreasing each time, getting less and less. And you do it all the way down to 8 feet below, run all those calculations, add them together, and that becomes your total rate of heat loss through the whole wall. Similarly, part B is determining it if it's insulated with an R value of about 12 hour degree Fahrenheit foot squared per BTU. So in that case, you're coming in to the column here and you're grabbing your values. We're going to do R 12.5. I'm pretty sure that this is a typo and it's supposed to say 12.5. We're going to go ahead and do that. Same exact process where we're dealing with the top here because we're not in metric. This column for your R values now, plugging everything in. Same temperature differential, same area, and you get 1,532 BTUs per hour. Now, everything else being equal, these two problems are identical except one's uninsulated and one does have insulation. And you'll notice that the insulation is 1/3 of the rate of the uninsulated. So it's making a pretty substantial difference to your overall heating load in that basement area. In similar vein for homework problems, looking at the heat transmission to soil around the perimeter of the building, using the equation Q, lowercase q as rate of heat transfer equals U sub F times L. The rate of heat loss, U sub F, is all here in a particular table for you to utilize. You just find what range your outdoor temperature falls in, and it will give you what value to put in for U. And then you just multiply it by the length of that perimeter part of wall. So in the example problem that's here, a commercial building is built on slab on grade foundation that is 120 feet by 48 feet rectangular. Assume the outside design temperature is -5 degrees. Determine the rate of heat loss through the exterior edge of the concrete slab. Well, your -5 degrees is going to fall into this middle row all the way across. And so the values that we use are all going to be coming from here. 60 for no insulation, 50 for R2.5, and 40 for an R5. Well, there are 3 parts, and you run it the same for each, one uninsulated, one at 2.5, and one at 5. So your lowercase q is going to be that U value in that row and column times your length, which is going to be the total perimeter of the building. 120 feet by 48 feet means you have 2 sides at 120 and 2 sides at 48. So you add that up and your total perimeter is 336 feet. You run it 3 times and you can get your answer each time. Pretty simple calculation. You just have to know where to go and look to find that table. The one cooling question that I'm going to go over right now is something I call the CLTD calculation method. That's cooling load temp difference. It's one of the methods that the textbook talks about. Much like the heating degree days, it takes the place of your delta T in your calculation. So Q equals U times A times CLTD. Now your CLTD value is tabulated from tables in your textbook. I don't have the textbook, so I can't point you to the exact references and show you a lot more examples because of it. But I'll help you work through this one based off of what's here. It seems that the tables may have some jumps in values. So if you have a number that falls in between 2 exact numbers, you're probably going to have to interpolate. There's some online interpolation things that you can help out with, or use your calculator to figure out what that CLTD value is. So this example problem, wood-framed single-family detached residence in Austin, Texas, has a south-facing wall with a net exposed area of 100 feet squared. The wall has an R sub T of 15.1 hour-foot squared degree Fahrenheit per BTU. Determine the sensible heat transmission component of the cooling load for this wall. So we're looking at our Q equals U times A times CLTD. Our U value is the inverse of our R sub T. So U equals 1 divided by 15.1. Our area is given to us in the question itself, exposed area of 100 square feet. So both of those values are already knocked out. The CLTD, according to this, it's in table 5.1 in your book. Your CLTD is going to be interpolated based on your orientation. So you're going to get that value based on a single family detached residence in Austin, Texas, which is hopefully a pretty clear and concise tabulation inside those tables. And based on 95 excuse me. Based on 95-degree outside design temperature, your CLTD is 16 degrees. For a 100-degree outside design temperature, it's 21 degrees. Interpolating between the two, you get a CLTD value of 19 degrees. So your U times A times CLTD is 0.066 BTUs per hour foot square degree Fahrenheit times 100 square feet times 19 degrees, which gives you 125 BTUs per hour. I will note as well, for separate cooling calculation problems, there are some that utilize Q in a not so positive way, where you're using Q as a value for the amount of airflow that's run through space. In the same problem, they use lowercase q for your heat loss. It doesn't go over a whole lot, but the numbers in front of that, it's 1.1 times your airflow Q times your temperature difference. that 1.1 has units that cancel out and make things nice and pretty for your airflow, which is measured in cubic feet per minute, or CFM. Just note that if it's asking for airflow, your uppercase Q airflow is a separate quantity than your uppercase Q temperature or total cooling load would be. So I am sorry the textbook uses that value, but be prepared that may come up and cause a little bit of confusion. I think there are example problems in the book that help go over several other ones, and homework should be roughly in this same range. If you keep in mind your Q equals UA delta T, that's going to take care of a lot of your questions back and forth. But like I said, we'll have some video or contact information that you guys can get in touch if you have further questions. Thank you very much for your time. I apologize again that I am not a professional public speaker, but I'm hoping that this does help bring a little bit of information from the real design world into the classroom and help point you in the right direction as you continue your studies. Thank you guys very much, and reach out if you have any questions again. Thank you.